Okay, we have two more forces we're going to talk about. We've got an applied force. That's going to be this force here, applied. And we use capital F with the little vector symbol above it with a sub A for applied. And apply is a push. So if we have a sled that's being pushed, so here we've got our sled, and assume that you can push it. So I'm going to go ahead and draw in a person pushing the incredibly large sled. All right. So this person's applying a force to the right on the sled. And the way we would represent that with a free body diagram is we would have the point of mass. We would put in our surface. And from the point of mass, we would show the direction that the force is acting on it. And so we're going to go ahead and put a vector to the right from the mass, right? And we label it F with an A for applied force. Okay, and then we have the last force. You've got a sled that is hanging on a wall in the garage, and there's no surface acting on this sled. There is just this tension on the rope that's on the sled. So the sled is actually being pulled upwards against gravity, and we use a capital T with the vector symbol above it. So our free body diagram would look like this. We'd use the point for the sled. There's no surface in this case. And I simply take my vector and I put it going upward with a capital T on it. So there's the tension force. Definition of tension force is the force within a taut string whoopsies. It can be a string, a rope, a wire, a chain, that holds it all together. By it, I mean the system together. Okay. The tension is constant throughout the string. So if I were to say that the tension on the string right there and compare it to the tension on the string right here, we would say that these two areas are the same amount of tension, meaning every part of that string or chain is experiencing the exact same force. So here are your lists of all your different forces. You have your weight force. Sometimes you can write it like this with a G. You have your normal force, your friction force, your tension force, and your applied force. We're going to learn a few more later on this year, but these are the main ones for this unit. Now we're going to put them all together because we're going to talk about a net force. So just for fun, we are going to put the sled on a surface that is an inclined surface, so down a hill. Okay, and the sled is not moving because of friction, so we have to put in all of our forces. I like to keep them color-coded, so my weight force is going to be my blue, my normal force is red, I'm going to keep friction as green, whoops, my applied force is going to be orange, if there is one, right? And my tension force I'm going to make pink. So I'm going to try and stay consistent with that kind of color scheme. Well, we're on Earth, so we definitely have a weight, and that goes straight down. All right? The surface is angled, so we want to make sure that we identify, okay, there's the surface, so I need to make it perpendicular for the normal force, perpendicular. The sled's not moving, so we've got friction holding it up. And we don't have any tension. I didn't say we're pushing it. So that is your free body diagram. And our net force would be found by simply adding up all of your vectors. So the sum of all vectors, or MA, right? And when I say the sum of all your vectors, it's not literally adding up N plus W plus friction. Okay, we'll talk about how we actually calculate that in class. But there you have it.